Hey everyone. So continuing our discussion of predictions in the context of logistic regression, we already mentioned kind of a complication compared to a basic linear regression model. The problem that we have as soon as we kind of make predictions in the logistic regression framework or in kind of any like non-linear generalized linear model framework is that the differences in predicted probabilities for a change in one variable, for example, a variable of interest, which we might call u, depend on the levels of all remaining variables included in the model. In this case, in this example, let's call them v. Okay, so the change for 1 unit change, or the predicted the difference in predicted probability that is associated with the change with a 1 unit change in a predictor of interest now fundamentally depends on the values of all the other predictors that are included in our model. And that, of course, raises the question of what should we have to keep those constant, but how should we keep them constant? At what value should we keep them constant in order to actually provide meaningful comparisons to evaluate the effect sizes based on our model? Okay. So one obvious alternative or one option could be to set all the remaining variables equal to some fixed value, for example, equal to the mean or equal to the median, right? And this, in a lot of kind of practical applications, this works quite well, but there can actually be problems with this kind of strategy, right? For example, we can run into problems when our input variables, those variables that we're kind of conditioning on and that we set equal to the mean or in the median or to the median, if those are very spread out or if those are bimodal or have some other kind of funky distribution, then setting them equal to the mean or the median might actually not really be a meaningful comparison, right? So we can run into problems where we compute predicted probabilities or changes in predicted probabilities for scenarios that are not even that are not really representative of what we observed in the data, right? And so to the extent that we want to actually communicate meaningful results, we have to kind of think about alternatives to solve this issue, right? In the textbook, there is a nice visualization that kind of illustrates this point, right? Think here of trying to compute the predicted probability of our or the difference in the predicted probability for a change in our variable of interest for u being equal to 0 to u being equal to 1, conditional on or holding constant our secondary predictor v, okay? And what you see here on the x-axis, we have our predictor v, and we have two different logistic curves for u being equal to 1 and u being equal to 0, okay? The point now here is that each of these individual tick marks basically indicate individual observations for v, okay? And imagine we have basically the same logistic curves, the same model for on the left hand side and on the right hand side. But in both cases, the distribution according to this variable v is slightly different, okay? Here we have a lot of, they're bimodal. Here we have a lot of observations down here and a lot of observations up here. And here the distribution of v is slightly different. We have a lot of observations down here and a lot of observations down here, okay? So now, despite the fact that the logistic curve, the model that we could fit through these data, look fairly similar, there are different kind of implications and predicted or changes in predicted probabilities for 1 unit change in u for different levels of v, okay? So again, the two alternatives that we're looking at is, on the one hand, holding the expected value, holding this v variable constant at, for example, the mean, at its expected value, okay? And we can talk, we can kind of think about what this implies in the context of these two visualizations, right? If we compute the expectation of v for the first case, this will be somewhere around here, assuming that there are roughly equal numbers of observations here and here. This will be around the center of these two bimodal, or of these kind of two sets of observations in this bimodal distribution, okay? And so now if we compute then the difference in the predicted probability of observing a 1 for u being equal to 1 and u being equal to 0, then we see that for the expectation of v, this is actually a very large change in the predicted probability, okay? So the predicted difference at or at the expectation of v is equal to 0.24. That's the difference around here between our u equals 0 and the u equals 1 logistic line, okay? Moving on to the right-hand side, we have a different distribution for v, and therefore also a different expectation of v. Now the expectation of v is again somewhere between those two kind of sets of observations, somewhere around here, okay? And if we look at the predicted difference for u being equal to 1 or u being equal to 0, at the expectation of v, we see that now, because we're kind of at the end of this logistic curve for the expectation, we see that this is actually, you know, a much smaller change in the predicted, the difference in the predicted probabilities, okay? So this value is much smaller, okay? Now, the problem here, of course, is that in both cases, this predicted difference at the expectation of v doesn't really represent any observations in our data that we have, right? We have both distributions are bimodal, sorry, and we don't have actual observations where v is equal to the expectation here or v is equal to the expectation here, right? So the alternative of just computing the predicted difference at the expectation is basically looking at all the different observations that we have, computing the predicted difference based on the model for u equals 1 and u equals 0 for each individual observation, and then averaging across those predicted differences in the probability, okay? So rather than taking the expectation and computing the predicted difference at that expectation, we're computing all the different predicted differences and then averaging the predicted differences. This is why we're calling this the average predicted difference, okay? And now we see for the first case, where a lot of observations here are at the end of this logistic curve that we estimate, or that we fit through these data, and a lot of observations are basically up here. We see that on average, across all different values of v that we observe in our data, the predicted difference for 1 unit change in u is actually quite small. It's actually just 0.03, right? Compared to that, here we have two sets of observations. If we look at the predicted, predictive, or the difference in the predicted probabilities across each of those individual observations based on the model that we fit, and then average across all those observations, we have a lot of observations right here in the kind of center of this logistic curve. So for each of those observations, the predicted difference is a lot larger, right? Between u equals 1 and u equals 0. So the average predicted difference is much larger, okay? And of course, which one is more kind of meaningful from a substantive perspective? Ultimately, the average predicted difference, because it's based on the actual observations or on the actual values in v that we observe, is a better representation of the actual kind of comparison that we're trying to make, namely between u equals 1 and u equals 0, right? So that being said, in many kind of applied examples, the difference between this average predictive difference up here across all observations, or the predictive difference at the expectation, is not really extremely large, right? But it's nevertheless something to keep in mind and to think about when you're making comparisons and when you're trying to evaluate your substantive effects, okay? And in general, the kind of solution and the recommendation is to use average predictive comparisons across all observations in the sample rather than just computing predictive differences at, for example, the expectation or the median. Okay, and we'll go through now in the last kind of a couple of minutes of this video, we're going to go through how we can do this based on our model results in R. Okay. We're going to work with one of the models that we worked with in the past videos, where we basically predicted Republican or vote choice for the Republican candidate in the 2000 US presidential election based on ideology and education, as well as the interaction between ideology and education. Okay, and now we're interested in basically examining the change in the predicted probabilities for different levels of ideology, okay, holding education constant, okay. And so the question now is, how do we hold education constant? Should we hold it constant at its mean, at its median, or should we just kind of look at all education values that we have in our sample and then average the predicted changes across those, okay? The first thing we do here is we set our values for the comparison in ideology. In our case here, we just look at a comparison between ideology or the feeling thermometer being equal to 2.5 versus minus 2.5, okay? So keep in mind here we're using this rescaled feeling thermometer, which ranges from -5 to +5, right? So this is kind of a change from, kind of a halfway change from minus 2.5 to 2.5 in a scale that ranges from -5 to 5, okay? So this is kind of a reasonable change in one of the predictors. And now if we want to evaluate how much this change leads to, or to what extent this change, or what the change in the predicted probability to vote for the Republican candidate that is associated with that change in our ideology score, we can basically follow both strategies that I outlined previously. On the one hand, we can make a central value comparison, which means we set education equal to some value, for example, the mean or the median, okay? If we want to kind of compute that change in the predictive probabilities, what we have to do is basically plug in our linear predictor for our values for high ideological self-placement and low ideological self-placement, but adding now the average value of education across the entire sample. Okay, and we plug those in with the respective coefficients, B3, as well as the interaction term, B4, okay, where we multiply the high values that we set with the average value of education, okay. We basically compute a predictive probability for our high ideology scale scenario and for our low ideology scale scenario, and then we compute the difference between those predicted probabilities, and the result here is 0.93, which again means that comparing respondents who place themselves at -2.5 versus 2.5 on this ideological feeling thermometer, if we compare those two sets of respondents, the probability to vote for the Republican candidate is 0.93 higher, holding education constant at its mean, okay? So this is the central value comparison. But again, education in this case, of course, is not really bimodal. We could just use the average, but in general, what we want to do is look at the average predictive comparison, right? So rather than setting our secondary variable equal to its average or its mean, what we do for the average predictive comparison is we basically specify the same linear predictor, but rather than just plugging in the average of our education measure, we're plugging in all sample values that we have in education in our data right here, as well as with the interaction term right there. And basically now compute a set of 1,000 or I don't know exactly how many observations are in our sample. I think around 1,200 respondents, right? So now we basically compute 1,200 predicted probabilities for ideology being equal to 2.5 and ideology being equal to minus 2.5, okay? And then we compute the difference in those predicted probabilities after plugging the linear predictor into our logit link function. And then we compute the mean across all those predicted probabilities. And the predicted, the change now is 0.89. So it's slightly smaller than the change in predicted probabilities that we compute based on our central value comparison, right? The change here in this specific example is of course not that large, but especially if you have predictors that are bimodal, there can actually, as we saw in the previous example here, there can actually be different conclusions based on whether you use average predictive differences or predicted differences at the expectation. Okay, so the strategy that is recommended is basically following the average predictive comparisons rather than the general central value comparison. The difference is always basically where you kind of compute this expectation. Here we compute the expectation in the predictor itself and then compute the predicted probabilities and the difference between those scenarios afterwards for just two different values for ideology. And here we take all the sample values of our predictor and basically compute a larger number of predicted differences in predicted probabilities and then average them afterwards. Okay, so basically we take the expectation at a later point in order to kind of get around this issue where our predictor is bimodal. Okay. Lastly, we want to, of course, incorporate estimation uncertainty when computing those predictions. So in the code that I showed you here, we're just using our point estimates based on our coefficients. But of course, we can take basically use the functions that we discussed in the previous video, posterior EPRED, or basically the draws from our posterior distribution, to take into account estimation uncertainty when we make these comparisons, right? And so here are basically the two examples to make both the central value comparison and the average predictive comparisons, now taking into account estimation uncertainty, right? Again, we're basically setting a set of values for our ideology measure, ranging from 2.5 to minus 2.5. And we're setting here a mean value, the expectation of our education measure. We take draws from our posterior distribution and compute the predicted probabilities and then compute the differences between both scenarios. And then we have a change in predicted probabilities as well as a 95% credibility interval. If we do this with the average predictive comparison, we basically have to take draws for each of those scenarios with not only the mean value of education, but basically for the full set of education values that we have in our data, in our sample. And then we compute these changes in predicted probabilities for each of those draws from the posterior distribution for each of those individual education levels that we actually observe. So there's a little bit more code here by basically rather than just creating this smaller tibble, we're basically selecting our predictors from our original data frame and then again using posterior EPRED to compute those predicted probabilities. But in the end, what we do is again predicting or computing the change in the predicted probabilities and computing 95% credibility intervals. Okay. So make sure to go through this code, and we're going to talk through another example in the Q&A session as well to make sure that you kind of get each individual one of those steps and also have a broad understanding of where the differences are between the central value comparison and the average predictive comparison. Again, the goal is to basically compute changes for scenarios that are actually meaningful, that are actually represented in our sample, And the better way to do that is to use the average predictive comparison rather than the central value comparison. Okay. All right, that's it for now. In the last video, I'm going to talk about residual plots for discrete data regression.